Hey everybody, this is WireDogSec back with another video for you guys. Today's video we are continuing on with the TryHackMe Cybersecurity 101 learning path. This is the networking module. This is the networking essentials room. Explore networking protocols from automatic configuration to routing packets to the destination. Hopefully you're all having an awesome day today and ready to learn. So let's go ahead and take a look at this room. Task 1, Introduction. Have you ever wondered how your computer can dynamically configure its network settings when you turn it on or connect it to a new network? Have you ever wanted to know how many devices and countries your packets pass through before reaching their destination? Are you curious how all your home devices can access the internet even though your ISP gives you a single IP address? If you want to know the answers to these questions, among others, then this room is for you. This room is the second room in a series of 4 rooms about computer networking, and you can see them down here. And we are currently in the networking essentials room. Learning prerequisites. To benefit from this room, we recommend that you know the following: ISO, OSI, model and layers, TCP/IP model and layers, Ethernet, IP, and TCP protocols. In other words, starting this room after networking concepts is the recommended approach, or you can check out my video. Learning objectives. The objective of this room is to teach you about various standard protocols and technologies that glue things together. You got dynamic host configuration protocol known as DHCP. You got address resolution protocol known as ARP. You got network address translation known as NAT. You got internet control message protocol, ICMP, ping traceroute. Get your notepad ready and let's begin. Task number 2, we're going to talk about DHCP. Give me my network settings. And let's see what it says here. You went to your favorite coffee shop, grabbed your favorite drink, and open your laptop. Your laptop connected to the shop's Wi-Fi and automatically configured the network, so you could now work on a new TryHackMe room. You didn't type a single IP address, yet your device is all set up. Let's see how this happened. Whenever we want to access a network, at the very least, we want to configure the following: IP address along with subnet mask, router or gateway, DNS server. Whenever we connect our device to a network, the above configurations must be set accordingly to the network or the new network. Manually configuring these settings is a good option, essentially for servers. Servers are not expected to switch networks. You don't carry your domain controller and connect it to the coffee shop Wi-Fi. At least I hope you're not doing that. Moreover, other devices need to connect to the servers and expect to find them at a specific IP addresses. Having an automated way to configure connected devices has many advantages. First, it would save us from manually configuring the network. This is extremely important, especially for mobile devices. Secondly, it saves us from address conflicts, i.e., when 2 devices are configured with the same IP address, an IP conflict would prevent the involved host from using the network resources. This applies to local resources and the internet. The solution lies in using dynamic host configuration protocol, which is DHCP. DHCP is an application level protocol that relies on UDP. The server listens on UDP port 67 and the client sends from UDP port 68. Your smartphone and laptop are configured to use DHCP by default. All right. D, discover. O, offer. R, request. And A, acknowledge. DHCP follows the 4 steps: discover, offer, request, and acknowledge DORA. And discover. The client broadcasts a DHCP discover message seeking the local DHCP server, if one exists. Offer. The server responds with a DHCP offer message with an IP address available for the client to accept. Request. The client responds with a DHCP request message to indicate that it has accepted the offered IP. Acknowledge. The server responds with a DHCP ACK message to confirm that the offered IP address is now assigned to this client. You can see that here in this graphic here. All right. The following packet capture shows the 4 steps explained above. In this example, the client gets the IP address not 192.168.66.133. You can see that here. T-shark -r DHCP yada yada yada. Okay, you see that in this PCAP file looks like. All right, discover, offer, request, and ACK. In the DHCP packet exchange, we notice the following. The client starts without any IP network configuration. It only has a MAC address. In the first and third packets, DHCP discover and DHCP request, the client searching for a DHCP server still has no IP network configuration and has not yet used the DHCP server's offered IP address. Therefore, it sends packets from IP address 0.0.0.0 to broadcast the IP address 255.255.255.255. As for the link layer in the first and third packets, the client sends to the broadcast MAC address of all Fs not shown in the output above. The DHCP server offers an available IP address along with the network configuration in the DHCP offer. It uses the client's destination MAC address. It used the proposed IP address in this example system. At the end of the DHCP process, our device would have received all the configuration needed to access the network or even the internet. In particular, we expect that the DHCP server has provided us with the following: the least IP address to access network resources, the gateway to route our packets outside the local network, a DNS server to resolve domain names. More on this later. All right. All right, got some questions down here. How many steps does DHCP use to provide network configuration? What is the destination IP address that a client uses when it sends a DHCP discover packet? What is the source IP address a client uses when trying to get IP network configuration over DHCP? So pause the video, go back and try to answer the questions yourself, and then come back to the video and we will continue on. All right, now let's see. How many steps does DHCP use to provide network configuration? And if we go back up here, it looks like 4 steps is going to be our answer. What is the destination IP address that a client uses when it sends a DHCP discover packet? Okay, and if we go back here, it's going to do the broadcast address. Okay, so let's go ahead and put this in there. And it says, what is the source IP address the client uses when trying to get IP network configuration over DHCP? Remember, that's going to be the zeros. Okay, so let's go ahead and copy and paste that in, and then we will continue on with the next one. Hey everybody, welcome back to my channel. Be sure to hit the like button, comment, and subscribe. Once you subscribe, be sure to hit that notification bell. All right, so you know every time I post a new video. As you can see here, most people that view my videos, view my channel, are not subscribed. Now, if you do subscribe, it will help me get into the YouTube algorithm so that we can continue to grow our glorious community here. As always, thank you all for taking the time to watch. Have a nice day and enjoy the video. Task 3, ARP bridging layer 3 addressing to layer 2 addressing. We have stated in the networking concepts room that as two hosts communicate over a network, an IP packet is encapsulated within a data link frame as it travels over layer 2. Remember that the two common data link layers we use are Ethernet and Wi-Fi. Whenever one host needs to communicate with another host on the same Ethernet or Wi-Fi, it must send the IP packet within a data link layer frame. Although it knows the IP address of the target host, it needs to look up the target's MAC address so the proper data link header can be created. As you would remember, a MAC address is a 48-bit number, typically represented in hexadecimal notation. For example, this one here and this one here are two MAC addresses on my network. However, the devices on the same Ethernet network do not need to know each other's MAC addresses all the time. They only need to know each other's MAC addresses while communicating. Everything revolves around IP addresses. Consider this scenario: you connect your device to a network, and if the network has a DHCP server, your device is automatically configured to use a specific gateway router and DNS server. Consequently, your device knows the IP address of the DNS server to resolve any domain name. Moreover, it knows the IP address of the router when it needs to send packets over the internet. In all this scenario, no MAC addresses are revealed. However, two devices on the same Ethernet cannot communicate without knowing each other's MAC addresses. As a reminder, in the screenshot below, we see an IP packet within an Ethernet frame. The Ethernet frame header contains the destination MAC address, the source MAC address, and the type IPv4 in this case. So you can see that here. All right. So let's go ahead and continue on. Address resolution protocol ARP makes it possible to find the MAC address of another device on the Ethernet. In the example below, a host with the IP address 192.168.66.89 wants to communicate with another system with the IP address of 192.168.66.1. It sends an ARP request asking the host with the IP address 192.168.66.1 to respond. The ARP request is sent from the MAC address of the requester to the broadcast MAC address, which is the all Fs, as shown in the first packet. The ARP reply arrives shortly afterwards, and the host with the IP address 192.168.66.1 responded with the MAC address. From this point, the two hosts can exchange data link layer frames. All right, here's an example what they're talking about here. If we use TCP dump, the packets will be displayed differently. It uses the terms ARP request and ARP reply. For your information, the output is shown in the terminal below. There we go. An ARP request or ARP reply is not encapsulated within a UDP or even IP packet. It is encapsulated directly within an Ethernet frame. The following ARP reply shows this. All right, there we go right here. ARP is considered layer 2 because it deals with MAC addresses. Others would argue that it is part of layer 3 because it supports IP operations. What is essential to know is that ARP allows the translation from layer 3 addressing to layer 2 addressing. All right, question time. What is the destination MAC address used in an ARP request? And in the example above, what is the MAC address of 192.168.66.1. So go ahead and try to answer these, then come back to the video to continue on. All right, the first one is going to be all Fs. Remember, it's that broadcast address. So if you scroll back up here, you can see that here. It says the ARP request is sent from the MAC address of the requester to the broadcast MAC address of all Fs here. All right, and the next one, we need to find the MAC address of this 66.1. If we scroll back up here, we can see that here in the packets right here. The 66.1 is at the following MAC address. You can also see it down here. All right. So there you go. Next task is task 4, ICMP troubleshooting networks. And let's see here. Internet Control Message Protocol, ICMP, is mainly used for network diagnostics and error reporting. Two popular commands rely on ICMP, and they are instrumental in network troubleshooting and network security. The commands are pinged. The command uses ICMP to test connectivity to a target system and measures the round trip time, RTT. In other words, it can be used to learn that the target is alive and that its reply can reach our system. Trace route. This command is called traceroute on Linux and Unix-like systems, and tracert on Microsoft Windows systems. It uses ICMP to discover the route from your host to the target. All right, you'll come across these commands quite often in your IT career. Ping. You may have never played ping pong, table tennis before. However, thanks to ICMP, you can now play it with the computer. The ping command sends an ICMP echo request, ICMP type 8. The screenshot below shows the ICMP message within a packet. Okay, so go ahead and take a look at this. All right, you can see all the information here, type 8 echo ping request, and see the rest of there. The computer on the receiving end responds with an ICMP echo request, ICMP type 0. Okay, and you can see that here, type 0. Right? Many things might prevent us from getting a reply. In addition to the possibility of the target system being offline or shut down, a firewall along the path might block the necessary packets for ping to work. In the example below, we use the -C4 to tell the ping command to stop after sending 4 packets. That's right, firewalls can block ping indeed. And you can see that here, this example, they're pinging this 11.1 IP address -C and then 4. You can see the following information here. All right, so 1, 2, 3, and 4. 4 packets transmitted, 4 received, 0 packet loss. The output shows no packet loss. Moreover, it calculates the minimum, average, maximum, and standard deviation (MDEV) of the round trip time (RTT). Trace route. How can we make every router between our system and target system reveal itself, also known as a hop? The Internet Protocol has a field called time to live, which is TTL, that indicates the maximum number of routers a packet can travel through before it is dropped. The router decrements the packet's TTL by 1 before it sends it across. When the TTL reaches 0, the router drops the packet and sends an ICMP time exceeded message type ICMP type 11. In this context, time is measured in the number of routers, not seconds. The terminal output below shows the results of running traceroute to discover the routers between our system and example.com. Some routers don't respond. In other words, they drop the packet without sending any ICMP messages. Routers that belong to our ISP might respond, revealing their private IP addresses. Moreover, some routers respond and show their public IP address, and this would let us look up their domain name and discover their geographic location. Finally, there is always a possibility that an ICMP time exceeded message gets blocked and never reaches us. So there's an example here, traceroute example.com, and you can see the other information right here. All right, it's going through that process. All right, so try this on your own machines and see what you can see in your environment. The traverse route might change as we rerun the command. That's right. So I think it's pretty much going to look for the most efficient path. All right. Using the example images above, how many bytes were sent in the echo ping request? Which IP header fields does the trace route command require to become 0? So try to figure out these yourself, then come back to the video, and we will continue on. Let's take a look here. And the echo ping request should be 40 if we're taking a look at these images up here. All right, so we're going to scroll up to the ping request right here, and then you scroll down to data, and it says 40 bytes. So that's going to be the answer to that one. And the trace route command required to become 0, remember that's going to be time to live, or TTL, because it decrements, right? So if we go back up here, we can see that right here. We're just talking about time to live stuff here. All right, and that should be it for that one. Task number 5, we're going to talk about routing. So let's see what they're talking about here. Consider the network diagram shown below. It only has 3 networks. However, how can the internet figure out how to deliver a packet from network 1 to network 2 or network 3? Although this is an overly simplified diagram, we need some algorithm to figure out how to connect network 1 to network 2 and network 3 and vice versa. So we can see what they're talking about here. Okay. All right, so let's continue. Let's consider a more detailed diagram. The internet would be millions of routers and billions of devices. The network below is a tiny subset of the internet. The mobile user can reach the web server. However, for this to happen, each router across the path needs to send the packets via the appropriate link. Obviously, there is more than one path, i.e. route, connecting the mobile user and the web server. We need a routing algorithm for the router to figure out which link to use. You can see that here, what they're talking about. The routing algorithms are beyond the scope of this room. However, we will briefly describe a few routing protocols so that you can become familiar with their names. You got OSPF, which is Open Shortest Path First. OSPF is a routing protocol that allows routers to share information about the network topology and calculate the most efficient paths for data transmission. And it does this by having routers exchange updates about the state of their connected links and networks. This way, each router has a complete map of the network and can determine the best routes to reach any destination. You got EIGRP, which is Enhanced Interior Gateway Routing Protocol. EIGRP is a Cisco proprietary routing protocol that combines aspects of different routing algorithms. It allows routers to share information about the networks they can reach and the cost, like bandwidth or delay, associated with those routes. Routers then use this information to choose the most efficient paths for data transmission. You got BGP, Border Gateway Protocol, which is very important. BGP is the primary routing protocol used on the internet. It allows different networks, like those of internet service providers, ISPs, to exchange routing information and establish paths for data to travel between these networks. BGP helps ensure data can be routed efficiently across the internet, even when traversing multiple networks. I recommend doing some Googling on BGP and look at the outages that have been caused due to BGP issues. You got RIP, which is Routing Information Protocol. RIP is a simple routing protocol often used in small networks. Routers using RIP share information about the networks they can reach and the number of hops routers required to get there. As a result, each router builds a routing table based on this information, choosing the routes with the fewest hops to reach each destination. Okay, question time. Which routing protocol discussed is in this task is a Cisco proprietary protocol? So go ahead and try to answer that yourself, then come back to the video. Okay, well, as we saw up here, it's going to be this EIGRP. So we're going to go ahead and copy and paste this down here, and we're done with this task. Next task is NAT. And let's see. As discussed in the network concepts room, we calculate that the IPv4 can support a maximum of 4 billion devices. With the increase in the number of devices connected to the internet, from computers to smartphones to security cameras and washing machines, hopefully your wireless machine isn't connected to the internet. It was clear that the IPv4 address space would be depleted quickly. One solution to address depletion is network address translation, which is NAT. The idea behind NAT lies in using one public IP address to provide internet access to many private IP addresses. In other words, if you are connecting a company with 20 computers, you can provide internet access to all 20 computers by using a single public IP address instead of 20 public IP addresses. Note, technically speaking, the number of IP addresses is always expressed as a power of 2. To be technically accurate, with NAT, you reserve 2 public IP addresses instead of 32. Consequently, you would have saved 30 public IP addresses. Unlike routing, which is the natural way to route packets to the destination host, routers that support NAT must find a way to track ongoing connections. Consequently, NAT supporting routers maintain a table translating network addresses between internal and external networks. Generally, the internal network would use a private IP address range, while the external network would use a public IP address. In the diagram below, multiple devices access the internet via a router that supports NAT. The router maintains a table that maps the internal IP addresses and port number with its external IP address and port number. For instance, the laptop might establish a connection with some web server. From the laptop's perspective, the connection is initiated from its IP address, this 0.129, from TCP router or TCP source port number 15401. However, the web server will see this same connection as being established from the 4.5 public IP address and TCP port number 19273, as shown in the translation table. The router does this address translation seamlessly. And you can see that here, see all these internal devices with these private IP addresses going to the router here, and it's getting NATed to this public IP address, which is the one provided by your ISP, and it's going out to the internet. So that's a public facing IP, okay? So remember that. And you have the little chart here or table here, all right? Question time. In the network diagram above, what is the public IP that the phone will appear to use when accessing the internet? And the next one is assuming that the router has infinite processing power. Approximately speaking, how many thousand simultaneous TCP connections can it maintain? So go ahead and try to answer these questions yourself, then come back to the video and we will continue on. So let's take a look here. What is the public IP that the phone will appear to use when accessing the internet? Well, remember, the internal IP addresses, the private IP addresses will be translated via NAT to this public IP address. Okay, so everything internally is going to be translated to this public facing IP address, okay, which is going to be this one here, this 4.5, and that's going to be the answer for that one. Next one is how many thousands simultaneous TCP connections can it maintain? Remember, there are 65,000 whatever ports out there, okay? I can't remember the exact number at the top of my head. So 65 is going to be our answer. And task number 7 is closing notes. And let's take a look here. This room introduced various protocols that we constantly use directly or indirectly. We have covered ICMP, DHCP, ARP, NAT, and routing. Although we use the internet daily without coming across most of this room's acronyms, these protocols are the foundation for a functional network. Question time. Click on the View Sites button to access the related site. Please follow the instructions on the site to obtain the flag. Okay, so go ahead and try that yourself, then come back to the video, and we will continue on. Okay, so let's go ahead and take a look at here, View Site. It says, which protocol do we need? As we have learned in this room, different protocols and techniques are used to solve various problems. In this exercise, we will help this computer get the information it needs. For each question, we need to select the protocol that best helps the question or answer the question. Okay, so go ahead and start. I want to find out the DNS server and default route on a network automatically. Which protocol should I use? All right, so it sounds like you're gonna have to use DHCP for this. So there you go. And I'm curious about tracing the route of packets as they travel to their destination server. What protocol would let me discover the path? All right, so you're going to be tracing. Remember, traceroute uses ICMP, so that should be the answer for this one. I want to confirm that I can exchange packets with another host as if I am playing ping pong. Which protocol supports this? Remember, ping uses ICMP. All right. I want to obtain an IP address to use and communicate with the other host on the network. What should I use? All right, so you want to obtain an IP address to use, so that should be DHCP. And there we go. Remember, DHCP automatically assigns IP addresses. So there's our flag, and we're done with that. And it says it's time to join the network core protocols. So that should be our next video. That completes this room. Hopefully, you all found this video of value. If you did, please consider hitting that like button. Subscribe to the channel if you're new here. Share the video. Comment below your thoughts, opinions, and information shared in the video. All right. Thank you all for taking the time to watch my video. Have a nice day, and I will see you later.